Hi, I'm Jannis Born from IBM Research. Everybody knows that language models struggle with numerical tasks. That's why we designed the number token loss. The NTL computes a regression-like loss directly on the token head of a language model. If you use the NTL on top of a cross-entropy objective, you can substantially improve performance on math and reasoning datasets without increasing runtime or sacrificing performance on non-numerical tasks. Many workarounds have been proposed to improve LLMs on math, like designated embeddings, reverting numbers, or chain of thought reasoning. But still, number representations in LLM sucks. We argue that this is because of the cross-entropy objective. It is nominal scale, treating numbers as words with no particular order. Basically, as you see on the right, when the label is a 4, predicting 5 and 9 gives equal loss, which makes 0 sense. NTL fixes this. For all number tokens in the vocab, NTL is an interval scale loss. For normal text tokens, it is always 0. Our key contribution is to compute NTL directly on the token head. We achieve this through giving the loss a one-time access to the tokenizer to extract a map between tokens, strings, and the numerical value floats. This way, the one token is mapped to its actual value 1. Motivated by optimal transport, we then calculate the Wasserstein 1 distance between the one-hot label distribution and the predicted distribution. We define the cost function based on the difference in the numerical value of the tokens. This loss, the NTL-VAS, emulates a regression head and can be even used for exotic cases like label smoothing or modular arithmetics. We also propose an alternative loss, the NTL-MSE, which is based on a dot product between the number token values and their assigned probabilities. We find that only the NTL-VAS aligns perfectly with human expectations on a numerical loss. First, unlike cross-entropy, both NTL flavors increase monotonically with mass on more distant number tokens. However, only NTL-VAS also has a unique minimum at the correct logit distribution. Now, my co-author Lars Penning from TU Munich will show you the results.
Hi, we can group our results into 6 distinct findings. First of all, NTL consistently improves performance on mathematical tasks. We have shown this with experiments on the DeepMind mathematical Q&A dataset, where we see that when training with NTL, our performance for both the interpolation and the extrapolation test set increases. Please note that whenever we talk about training with NTL, we actually use cross-entropy and number token loss jointly. Next, we have shown that NTL performs regression tasks as good as the regression head. And for this, we have carried out experiments on the RJokes dataset, where we input a text paragraph and predict a single float. We have validated that when training language models that operate with discrete tokens with the number token loss, we can actually catch up to models that carry a dedicated regression head. Third, NTL is effective across architectures. For this, we have fine-tuned the IBM Granite as well as GPT-2, which are decoder-only models, on a multiplication dataset. We have again seen that our performance increases, particularly in the extrapolation setting, which corresponds to the last row and column in these matrices. Furthermore, we have seen that NTL does not impact performance on standard language modeling tasks. For this, we have carried out experiments on the text-only dataset multi-RHC, where we have seen that our performance does not decrease when using the number token loss. This can be attributed to the fact that NTL is only used on the number tokens, while for all other tokens, standard cross-entropy is used. Moreover, computing the number token loss is fast. Computing NTL is around 50 times faster than regular cross-entropy, because we only consider a very tiny subset of all tokens. Thus, compared to training with cross-entropy only, the time for full training step only increases by 1 to 2% when also using NTL. Consequently, the NTL computation overhead is pretty much negligible. Furthermore, NTL scales to the size of large language models, and we have shown this with an experiment on the complex reasoning dataset GSM-8K with a T5 3 billion parameter model. To summarize, NTL enhances the language model's capability to handle numerical data up to a point where we can perform on par with a regression head, and at the same time we do not compromise text-only tasks. NTL scales to larger models, is model agnostic, and pretty much plug and play for any model. Thank you very much for your attention.